So we have seen the reason behind convection happening in fluids, where we talked about thermal instability, and convection comes into picture when your Rayleigh number gets larger than a critical Rayleigh number, and that is when the system becomes unstable, where buoyancy force takes over the viscous force, right? And convection begins in a system, right? And we talked about critical Rayleigh number in different conditions. And in nature, what happens is Rayleigh number is usually much greater than Rayleigh number critical, because the length scale that we deal with are generally very large, or the thermal diffusivity or kinematic viscosity generally is very small, and that is why the Ra value that we get is much greater than critical Rayleigh number. In fact, we usually get critical Rayleigh number in range of 10 to the power 10 or something, right, which is much greater than a critical Rayleigh number for the cases that we discuss, at least. And that is why it's very easy to observe convection in nature. So today we are going to see different kinds of convection in nature that occurs, and how, what kind of analysis we have to perform, or how to, let's say, find the final temperature or depth of convection, etc., for this kind of flows. So we are going to see. So these are two different kind of convection we have. These are basically broad classification of convection in nature, right, where one is called top to bottom convection and other one is called penetrative convection. So top to bottom convection is something like this, where we assume that this is a fluid layer of depth h, okay, and when convection happens, so we are heating it, right, we are supplying some heat, let's say that is q, that is the heat flux per unit area per unit time. So this heat that we supply actually creates convection, and complete layer of the fluid which you have here, they come under the effects of convection, okay. And we assume that this is the fluid boundary at the top, so complete fluid is under the effect of convection, okay. So that is called top to bottom convection, where after some time, after heating for some time, temperature starts rising for complete fluid layer, not just for the bottom layer or something like that, right? So, and this is in fact the kind of convection we considered previously in the last lecture, when we defined a fixed thickness for the fluid layer, and we tried to study critical Rayleigh number, etc. Okay, but then there is another type of convection that is called penetrative convection. That is much more common in nature, and that you might also have seen it in different locations. Okay, so one of the examples are shown here, where you can see these air parcels rising from different locations upward, right? So this is happening, let's say, in the early morning when sun rises and it starts hitting the surface, right, the earth's surface, and the air molecules that are in contact with the earth's surface, they start getting heated up, right, and when they start getting heated up, they become buoyant, and now they start rising slowly because they have got buoyancy. So convection begins, and all these air parcels start going upward because of the buoyancy force, and they start going upward against the gravity, right? So this convection is happening when it starts getting heated up. But what happens now is, this fluid layer that we are talking about, let's say this is the, it starts from here, and this is the atmosphere, and this goes all the way till really large depth, right, which h can be considered in fact infinity, compared to uh, the layer of convection that we get, right? And that is why the convective layer that we get may be up to certain depth. Let's say this is 100 meter for instance, but the total h that is going, that might be much greater than 100 meter, or let's not give a fixed value here, but let's call this is h. Okay, so the capital H, which is the atmospheric layer or depth, is usually much greater than h, where h here is this one, can be called the atmospheric uh, depth, where this h is can be called the convective depth. Okay, so in this case your capital H is much greater than smaller h, where smaller h is under the influence of convection, and capital H, complete capital H, is not under the influence of convection, right? And that's why these are called penetrative convection, because it's penetrating into the complete layer but is not able to go completely fully. Whereas for the left hand case, here it can be assumed that H is same as capital H, right? H is under the convective zone, and capital H is the total fluid layer. Okay, so for top to bottom convection, this is the condition, whereas for penetrative convection, this is the condition. Okay, so let's start with top to bottom convection, and this is much simpler to analyze because we are dealing with complete layer of fluid, and we will then go to more interesting case of penetrative convection. Okay, so in this case, let's assume that we have this is a solid boundary and we have a fluid layer, right? And we start giving some heat, which is Q, which is again heat flux per unit surface area and per unit time. Okay, and let's consider that T naught is the original temperature of the fluid layer before heating. Okay, so that is temperature the fluid has before we start heating, and we want to find what is the new temperature after heating, and we assume that the layer thickness is h, and as we discussed in the last slide, h here is same as h, small h is same as capital H, where small h is the convective layer and capital H is the fluid layer, and here both the convective layer and fluid layer are same. Okay, so convective layer H is same as fluid layer capital H. Okay, so in this case, if we want to find the rise in the temperature, we can simply define it as dt over T, that is the rate of change of capital T, that is the temperature with respect to time. This will be Q over rho Cp times H. Okay, so that is the rise in temperature of the fluid per unit time, right? Which can, if you integrate it, it can simply give you Ts T naught plus Q over rho Cp H times T if Q is constant on time. Okay, if your rate of heat flux is constant. If it is not, then yes, we have to consider it time effect as well. So here T naught is the original temperature, Q is the heat flux per unit surface area per unit time, and then we also have rho, that is the fluid density, and Cp is the specific heat of the fluid, right? And these are the properties that we have already discussed in the past, and that is why we are not discussing them again. And H is the fluid layer depth. Okay, so this equation is very simple. If you know what is the heat flux you are giving, and if you know the original temperature, you should be easily able to find out the rate of change of fluid temperature with time. And here this can be considered as T as a capital T as a function of time. So okay, where capital T is the temperature and small t is the time. All right, I think I need to just be very specific here. So capital T is the temperature and small t is the time. Okay, and this time is measured from the time when we start heating it. All right, so this is top to bottom convection. But now let's go to penetrative convection and understand how it happens in the atmosphere, and what kind of analysis we have to do. So as we discussed, penetrative convection starts at the bottom like here, and it can only go up to certain depth. Let's say that is capital H, that is small h, and the fluid layer depth is capital H. So small h is much smaller than capital H, right? Where this is called, so H is of the convective layer, which in case of atmosphere is also known as the atmospheric boundary layer, ABL. Okay, so this is a common term that is used for convective layer in case of the atmosphere, and H here is the fluid layer, which basically is the atmospheric thickness, right? And capital H is much greater than small h, and that's why we don't really have to worry about capital H. We just want to find what is the small h with respect to time. Okay, so this is something that you have seen in the atmosphere, which is quite common. And what exactly happens here is, originally water temperature you had in the air that will slowly rise as it starts heating up, right? And this particular cycle, let's say, happens both on a daily basis as well as on a seasonal basis. So on a daily basis, at night the air gets cooled, and in morning it starts getting heated up slowly, right? So that is on a daily basis. As well as when we talk about the seasonal effects, when you go from winter season to summer season, then also the average temperature of the layer increases slowly. Okay, so in the, you can also say that on a daily basis you get this cycle where temperature comes down, rises again for the atmospheric boundary layer. Whereas in case of seasonal effect, you can say this goes something like this, right? So on this one you can call is the daily cycle, whereas this one is the seasonal cycle. Okay, it may not really be accurate, but this is how it happens on a daily basis. Air gets cooled and heated up, and the thickness is generally very small for a daily basis cycle, whereas as you go from one season to another, the thickness obviously gets greater, and also the temperature difference increases. Okay, so this is something we will see. And then we also have similar kind of convection in case of lakes and oceans, right? In case of atmosphere, we consider the heating up of the atmosphere from the bottom. In case of lakes, generally the other type of convection happens. So let's assume that this is the water layer, okay, and then we have maybe a depth h which may be in several 100 meters or even in kilometers in case of oceans, right? So in now during winter, when there is already certain stratification or temperature in the water, in during winter the atmospheric temperature goes below the water temperature. So what happens is you start supplying heat from ocean or lakes into the atmosphere, and that is why once you supply heat, the upper layer of fluid actually it starts getting cooler compared to the lower layer, right? If upper layer of fluid starts getting cooler, what happens is its density increases compared to the lower layer, and that is why this fluid now, the cold water now starts going downward, right? So here this H red color you see is the heat that is getting away from water into the atmosphere, right? Okay, and whereas once this heat goes into the atmosphere, water gets cold, and slowly this heavier water which is on top of lighter water now, that goes down, and that is why this boundary layer, convective boundary layer, forms in case of lakes and oceans. Okay, so this convection that happens, that again works as a mechanism for heat exchange in the ocean or regulating the temperature throughout the ocean. And in fact there is some data available here for subarctic Pacific Ocean from these authors, and you can see how the heat heat flux per unit on a daily basis for this particular case is, you can see how the heat flux increases and then decreases. So in the during the winter time you have heat flux going out from the water to the atmosphere, whereas during summertime heat is coming in uh, into the water, right? So this probably is summertime when water is getting heated up, and this is during the winter time. So regardless, your because of this atmospheric summer heating and cooling of the ocean water, the temperature of the ocean itself goes up and down, right? And that is why what you see here in this particular figure is different contours, and each contour is showing you temperature in Fahrenheit, and you can see the thickness layer if you consider in like different months, the size of this boundary layer actually increases, right? So it has certain depth, it gets deeper and deeper with time, and especially during the winter months you can see how this thickness that you see is actually, so if you start somewhere from August, here the depth generally goes slowly down with time, right? And as you come from here again slowly it decreases. So what's happening is during winter time, as we discussed, the heat is getting released into the atmosphere, and that is why this convection builds that we discussed here. And as convection builds, the temperature of higher and higher level layer actually comes under the convective zone, and that's why they start getting the same constant temperature, right? And you can see the temperature in general decreases with time, and then towards the winter it decreases more, and as it goes towards summer, which is presented by this plot, it slowly increases again. Okay, so this penetrative convection that we are talking about happens both in case of lakes and oceans and also in case of atmosphere. Just the reverse happens in atmosphere. So atmosphere, it happens during the summer season or during the daytime, right, when the bottom surface starts heating up, whereas in case of lakes and oceans, this convection, penetrative convection, happens during either at night or winter season. Okay, so night can be considered as the daily cycle, and this one can be considered as the seasonal cycle, right? Whereas in case of atmosphere, it happens either during day or summer, right, as we discussed, where day belongs to the daily cycle and summer belongs to the seasonal cycle. Okay, where this can be called daytime and this can be called summertime. Okay, so I hope that is clear what's happening here. And now we have to talk about the stratification that is there in the system. So what happens is, let's consider before convection begins, right, before the day starts or before the summer starts, there is usually stratification in the medium. So if you measure from the bottom, this density of the fluid is actually, or temperature, let's talk about the temperature generally increases as you go up. So if T naught is the surface temperature before convection begins, T at any point Z is usually T naught plus gamma Z. Okay, so basically T naught is at Z equal to 0. Okay, where T of Z is at T naught plus gamma Z, and we assume that your if you consider this to be Z axis and this to be temperature, your temperature will slowly rise. So this is your, or in other words we can say, temperature will go from this point onwards, where this can be considered as T naught and this will be T naught plus gamma Z. Okay, the way Z rises, and then you can find the slope for this line, right? Okay, so this is the original condition before heating starts or before convection starts. So usually we are talking about this boundary layer in several hundred meters or kilometers. So it's very common to have stratification in the atmosphere, especially when we experience, if you are on the ground floor, on the just at the surface you have different temperature. As you go to the fifth floor of the building or top floor, you will see slight difference, but here we are talking about several hundred meters or kilometer. So this stratification is much more common in that length scale. Okay, and here we have already talked about stratification frequency, if you remember, that we name as n square, and that earlier we talked about these in terms of density, but here we will consider this in form of temperature only, and that can be defined as dTi over dz. Okay, where dTi is the temperature before convection begins, and this can be simply written as gamma G gamma. Okay, where gamma here is dTi over dz. Okay, where Ti is simply T of Z at T equal to 0, right? That is before convection begins. Okay, so Ti is the temperature at different elevation before convection begins. So that's why we consider it T equal to 0. So time T equal to 0, right? And this is the stratification frequency. We have stratification frequency. That is something we have talked about in the past. This gives us this capital gamma, which you can call as stratification slope, right? That gives you the slope of the curve. So basically this will give you slope of this straight line, right? So this is now the temperature uh, which we can actually, this can also be written as T of T of Z at T equal to 0, right? So that to make it more clear, so vertical temperature before convection, right? So this is the temperature profile we have for in the atmosphere before convection begins. So we can also call it the initial temperature. Okay, so Ti here is also known as the initial temperature. Okay, so this is the temperature profile we have. And now what happens when we start heating up? Obviously this stratification slowly goes away and we start getting a particular temperature profile in the system, and that goes into a convective layer. So what was originally stratified becomes more like a convective layer. Okay, so if we again consider this example where we have this convection happening, so with time, at let's say time t equal to t1, this layer of the fluid has come under the convection, and this will actually achieve a constant temperature. So let's say that is capital T, capital T1. Okay, but with time t2, this layer will have risen up. Okay, so now the at time t equal to t2, you have got a thicker layer, and now this complete layer, not just the upper layer, but this complete layer will be with temperature t2. Okay, and we will call the original the thickness here at time t1 is h1, thickness at time t2 is h2, where this is basically z equal to h1 and z equal to h2, where z is measured from the bottom here. Now with further increase in time, this convection continuously happens, it continues, right? And that is why this thickness of the convective layer increases further. So here you can call z equal to h3 and temperature equal to t3, and this temperature, sorry, time t equal to t3 and temperature has become t3. So this is now complete layer is under that temperature T3. Okay, so here you can assume that your T3 is greater than T2 is greater than T1, where T1, this is actually greater than Ti, that is the initial temperature, right? Because of convection, this whole layer is slowly getting heated up. Okay, and with time. So basically this H3 is also greater than H2 is greater than H1. So H, that is the convective layer, uh, thickens with time, right? So the layer of the thickness of the layer slowly increases with time, and also your temperature, uh, so convective layer temperature increases with time. Okay, and for the convective layer we can consider the temperature to be constant. Okay, so T is considered constant for the convective layer. Okay, so this is one example shown here. So this image that you see at bottom right, that shows you an original stratification. So this is the Z that is measured from the bottom, right? This Z goes this way, and your temperature is measured from here, and this one can be considered as delta T. And originally this was the stratification, right? That is that gives you the slope as the sigma. Sorry, I was calling this as lambda, but that's actually sigma. Okay, so that was the original temperature. This gives you the Ti, right? But with time you can see how this temperature is slowly increasing, and the thickness of the layer is also increasing. So you can see this is sort of H1, this is H2, this is H3, this is H4, etc. And the temperature for this H1 can be seen that has become T1. After H2 it has become T2, etc. Right? So with time H increases, and also T increases, right, for the convective layer. All right, so this is what happens as time increases, your convective layer thickness increases, and with that your temperature for that particular layer becomes constant. So as you can see here, the temperature is constant, right? That is T equal to constant, where before convection this was increasing, right? It had a profile which was a function of Z. So T here is not a function of Z for time greater than 0, right? Whereas here T here is function of Z at T equal to Ti, right, at initial time. All right, so this is what happens for convection, and we are going to analyze this in more detail. We want to find out what is the rate of change of thickness with respect to time, and what is the temperature of that convective layer with respect to time for this penetrative convection.